Imagine complete and total darkness. Not the darkness of a room with the lights off, not the darkness of a cloudy night. Something far more absolute. There is no space yet. There is no time yet. There is nothing. And then, in a single instant that defies every intuition you have ever had about the nature of reality, everything that will ever exist erupts into being from a point smaller than anything you could possibly conceive. The temperature is not millions of degrees, not billions. Try 10 to the power of 32, a number so large it has no meaning in any language humans have ever spoken. This is not a metaphor. This is what the physics tells us actually happened, approximately 13.8 billion years ago. And in the 3 minutes that follow, just 3 minutes, the entire cast of the universe's first story is assembled. But here is what nobody tells you in school. In those first 3 burning minutes, something impossibly delicate is born.
Something that will one day sit in your pocket, power your car, calm a troubled mind, and nearly end human civilization. Something so light it floats on oil. Something so reactive it hisses and sparks at the mere touch of water. The universe, in its very first act of chemistry, creates lithium. And then, almost immediately, it starts to disappear. Remember that. Remember the flame that made everything now rests quietly in your pocket. Because that tension between the colossal fire of creation and the fragile, silver-white sliver of metal it left behind is the whole story of this element. It is a story of cosmic mystery and human obsession, of healing and destruction, of a resource so ordinary-looking that you could hold it in your hand and feel absolutely nothing, while somewhere beneath the Andes Mountains, ancient lakes are slowly dying to put it there. Lithium, atomic number 3, the third lightest thing in existence, the oldest solid that ever formed.
And quietly, without any fanfare, the invisible axis around which the 21st century now turns. Let us start at the very beginning, because with lithium, the beginning is not a metaphor. It is a literal, physical, cosmic event, and understanding it changes how you see the metal entirely. In the first fraction of a second after the Big Bang, the universe is a soup of quarks and gluons, the subcomponents of protons and neutrons, too hot and too energetic to stick together into anything coherent. But as the universe expands, it cools. Within the first second, protons and neutrons begin to form. Within the first 3 minutes, those protons and neutrons begin to fuse. This process is called Big Bang nucleosynthesis, and it is the first time in the history of the universe that atoms, or at least the nuclei of atoms, are assembled. The recipe is brutally simple. Roughly 75% of all the matter produced is hydrogen, a single proton, the most basic thing you can build. About 25% is helium, 2 protons, 2 neutrons. And then, in trace amounts so small they seem almost accidental, lithium-7 is forged. 1 atom of lithium for every 10 billion atoms of hydrogen. That is not a typo, 1 in 10 billion. The universe made lithium, but it barely bothered. And here's the first knot in the mystery, a knot that has kept astrophysicists awake for decades. The mathematics of nucleosynthesis is extraordinarily precise. Scientists can calculate, with remarkable confidence, exactly how much helium the Big Bang should have produced. And when they look out at ancient stars, the numbers match almost perfectly. But when they do the same calculation for lithium, when they predict how much lithium-7 should exist in the oldest stars in our galaxy, the ones that formed before any supernova ever scattered new elements into the cosmos, the prediction and the observation do not match. The models say there should be roughly 3 times more lithium in those ancient stars than astronomers actually detect. 3 times more. And nobody knows where it went. This is not a minor rounding error. This is a fundamental discrepancy at the heart of one of the most successful theories in all of science. The universe, it seems, has been quietly eating its own history, and lithium is the missing page. So where did it go? This question sounds almost casual until you sit with it long enough to feel its weight. We are not talking about a laboratory measurement going slightly wrong.
We are talking about looking out across billions of light years of space, examining stars so old they formed when the Milky Way itself was still assembling, and finding that a third of the primordial lithium the universe should have made is simply not there. Astronomers call this the cosmological lithium problem, and it is one of the most stubborn, unsolved puzzles in modern astrophysics. Let us walk through what we actually know, because the story of what we do not know becomes more fascinating once you understand the landscape. When astronomers want to study the earliest chemistry of the universe, they look for what are called metal-poor stars. In the language of astrophysics, anything heavier than helium is a metal, which means that stars with very low abundances of iron, carbon, and oxygen are the oldest ones, formed before generations of supernovae had time to seed the cosmos with heavier elements. These ancient stars, clustered in the diffuse halo of the Milky Way, are like fossils. They have changed relatively little since their formation billions of years ago. Their outer layers preserve a chemical snapshot of the early universe. When you aim a spectrograph at one of these halo stars and analyze the wavelengths of light they emit, you can read their composition like a label on a bottle. And what astronomers found, beginning in the 1980s with the work of Monique and Francois Spite, was a remarkable thing. Across a wide range of these ancient stars, the lithium abundance is nearly constant. No matter how old the star, no matter how metal-poor, the lithium sits at approximately the same level. This plateau, now known as the Spite Plateau, is itself a beautiful piece of evidence for Big Bang nucleosynthesis. It says that yes, lithium was made in the Big Bang, and yes, these stars preserved it. But the plateau sits stubbornly at a level about 3 times lower than what the standard model of nucleosynthesis predicts. 3 times. Every star you look at tells the same story. The lithium is missing, and it is missing consistently, which means whatever happened to it happened universally. So what are the suspects? Astronomers and physicists have proposed several explanations, and each one opens a door into something stranger than the last. The most straightforward possibility is that the stars themselves destroyed their own lithium. Stars are not inert containers. They are dynamic, churning objects, and if mixing processes in the outer layers of these ancient stars slowly pulled lithium down into hotter interior regions, it would be destroyed by nuclear reactions, converted into helium at temperatures above 2.5 million degrees. This is called lithium depletion, and some theoretical models suggest it could account for much of the discrepancy. The problem is that the models produce a spread of lithium abundances, because different stars should deplete at different rates depending on their mass and rotation. But observations show that remarkably tight Spite Plateau, not a scatter. Whatever process is at work, it acts with eerie consistency. Another possibility goes in the opposite direction entirely. What if the standard model of nucleosynthesis is slightly wrong? What if there is some new physics, some interaction between particles in the early universe that we have not yet discovered, that suppressed lithium production below what the standard model predicts? This is where the problem gets genuinely exciting, because it opens the door to physics beyond the standard model. Some researchers have proposed that dark matter particles in the early universe could have interacted with the lithium nuclei and disrupted their formation. Others have suggested that a variation in the fundamental constants of physics during the Big Bang could have altered the reaction rates. None of these ideas have been confirmed, and many have been ruled out, but the fact that they are being seriously considered tells you something important. The lithium problem is not just a bookkeeping error. It might be pointing at something genuinely new about the nature of reality. And then there is a third possibility, one that is in some ways the most unsettling. What if some of the missing lithium was produced later, not in the Big Bang, but in cosmic ray spallation, the process by which high-energy particles smashing through interstellar gas can create light elements like lithium, beryllium, and boron? And what if our estimates of how much cosmic ray lithium exists in those ancient stars are off? The numbers get complicated very quickly, and the more you dig, the more you realize that lithium sits at the intersection of cosmology, nuclear physics, and stellar astrophysics in a way that very few elements do. It is not just a building block, it is a test. It is a probe of the first minutes of time, and the fact that the probe gives us a confusing answer is not an embarrassment, it is an invitation. So the next time someone tells you that cosmology is a finished science, that we understand the Big Bang in complete detail, remember the Spite Plateau. Remember those ancient halo stars, quietly holding their lithium secret for 12 billion years, waiting for us to develop good enough instruments to notice that something is wrong. The universe made this element in a quantity we cannot fully account for. And every old star we look at whispers the same quiet question. Where did it go? We do not know. Not yet. What we do know is that whatever lithium the universe made, it managed, against tremendous odds, to survive the violent history of galaxies and solar systems and find its way into the rocks of a small, unremarkable planet orbiting a middle-aged star in a quiet spiral arm. And once it arrived here, it began a second life, one no less strange than the first. Picture a coastline in the South Atlantic in the year 1800. The air smells of salt and tropical vegetation. The island of Uto rises from the water off the coast of what is now Brazil, and on it, a man named José Bonifacio de Andrada y Silva is doing something that very few people in the world could do at that moment in history. He is looking at rocks and seeing chemistry. Bonifacio was not your typical mineralogist. He was a Brazilian Portuguese statesman, a poet, a naturalist, and one of the most educated men of his age, having studied at Coimbra and traveled across Europe learning from the greatest scientific minds of the Enlightenment. On the island of Uto, he encountered a mineral he had never seen before, a pale, translucent stone with a pearlescent luster that would later be named pedalite, from the Greek word for leaf because of the way it cleaved in flat sheets. He collected samples and noted something peculiar. When you threw a fragment of pedalite into a flame, it did not burn with the familiar yellow or orange of most minerals. It burned a vivid, almost violent crimson, a color so distinctive, so unlike anything the flame of a candle or furnace normally produced, that it was clearly announcing the presence of something new. Bonifacio brought his samples back to Europe and shared them with the scientific community, and the stone began its slow journey through the laboratories of the early 19th century. For 17 years, it sat on shelves and in collections, analyzed, admired, but not fully understood. Then, in 1817, a young Swedish chemist named Johann August Arfwedson was working in the laboratory of the great Jöns Jacob Berzelius, the man who invented the modern chemical notation system, who gave us the symbols H, O, N, and C that still appear on every chemistry classroom wall in the world. Arfwedson was analyzing a sample of pedalite, attempting to account for all the elements it contained, when he ran into a problem. The numbers did not add up. He could identify silicon, oxygen, and aluminum, the usual suspects in a silicate mineral, but when he totaled everything up, there was a gap. A small but definite percentage of the mineral's mass was unaccounted for. Something was there that he could not name. With the methodical patience that defines great experimental chemistry, Arfwedson began to investigate. He treated the mineral with acids, he precipitated compounds, he performed titration after titration. And gradually, he isolated what appeared to be a new alkaline substance, similar in its chemical behavior to sodium and potassium, but different in ways he could not quite explain. It formed salts, it reacted with water, but its behavior was subtly, tantalizing off, lighter than either of its chemical cousins, producing compounds with different solubilities and melting points. Berzelius, examining Arfwedson's results, named the new element lithium, from the Greek word lithos, meaning stone, because it had been found in a mineral rather than in plant ashes, the way sodium and potassium had been discovered. The name was meant to reflect its rocky origin. And here is the first great irony that lithium carries like a birthmark. The most stone-like name in the periodic table belongs to a metal so light that it floats on water. Actually, let us be more precise about that, because the truth is even stranger than the cliché. Lithium does not merely float on water, it floats on oil. Its density is just 0.534 grams per cubic centimeter, which means it is literally less than half as dense as water. You could place a piece of lithium in a bowl of olive oil and watch it sit on the surface like a tiny gray island. Of all the solid elements, only two are less dense than water. lithium, and a very rare element called francium. And frankly, francium barely exists long enough to measure. For all practical purposes, lithium is the only metal that floats. But here is where the story gets dangerous, because you absolutely cannot demonstrate that by placing lithium in water. And this is the second great irony. A metal so light it floats is also so chemically aggressive that contact with water causes it to immediately react, releasing hydrogen gas and generating enough heat to ignite that hydrogen in a fizzing, spitting, occasionally flaming display that bears no resemblance to the quiet buoyancy you might expect from something bobbing on the surface of oil. This is not a gentle chemical reaction. Arfwedson himself would have witnessed early demonstrations of lithium's reactivity and understood immediately that this new element was unlike anything chemistry had cataloged before. It was an alkali metal, yes, in the same family as sodium and potassium, but being the lightest of the three, it concentrated all of their volatility into the smallest possible package. Every atom of lithium has 3 protons and 4 neutrons, holding a single valence electron so loosely that it leaps away at the first opportunity, bonding furiously with whatever electron-hungry partner presents itself. Water, oxygen, nitrogen, lithium reacts with all of them. Leave a piece of lithium in open air and watch it slowly develop a gray-black coating as it converts to lithium oxide and lithium nitride. This is why, even in the early 19th century, chemists quickly learned that lithium had to be stored under mineral oil or in sealed containers. Even today, if you order a small sample of lithium for a laboratory, it arrives submerged in a hydrocarbon solvent, protected from the air it would otherwise devour. There is something deeply poetic about that. The most primordial solid in the universe, one of the first things ever assembled from the wreckage of the Big Bang, so desperate for connection that it cannot even sit on a table without attacking the air around it. Arfwedson isolated the oxide and various salts of lithium, but he never managed to isolate pure metallic lithium itself. That feat fell to Humphrey Davy and Wilhelm Brand in 1821, who used electrolysis, passing an electric current through molten lithium compounds to finally obtain the gleaming, silvery white metal. Davy was no stranger to this technique. He had used it to isolate sodium and potassium just a few years earlier, and lithium proved similarly cooperative when subjected to electrical persuasion. What they obtained was astonishing to look at. In its pure form, freshly cut, lithium has a bright, almost mirror-like surface, silver white and slightly lustrous, not unlike aluminum, but softer, far softer. This is the third irony, and perhaps the most disorienting one. Lithium is a metal, but it is so soft that you can cut it with a kitchen knife. Its hardness is roughly comparable to soft cheese, perhaps slightly firmer. If you squeezed it, not that you should because of the aforementioned reactivity, you could deform it with your fingers. The hardest thing about lithium is keeping it solid enough to study. The history of its discovery is, in miniature, the history of chemistry itself in the early 19th century, a period when the periodic table was being assembled piece by piece, when each new element was a revelation, a proof that the world was more varied and surprising than anyone had imagined. And lithium, with its combination of extreme lightness, extreme reactivity, and unexpected softness, was more surprising than most. But the young Arfwedson, bent over his beakers in Berzelius's Stockholm laboratory, could not have known that the faint crimson flame dancing above his experiments was not just a pretty anomaly. It was the signature of a substance that would one day bend the arc of history. That delicate, almost bashful little flame, that was the beginning of everything. High in the Atacama Desert of northern Chile, there is a place that looks as though the earth has forgotten to finish itself. The ground is white, not the white of snow or sand, but a hard, crystalline white that crunches underfoot and reflects the equatorial sun with an intensity that forces you to squint even through dark lenses. The sky above is a shade of blue so saturated it looks artificial. There are no trees. There are no buildings on the horizon. There is almost no sound except the occasional hiss of a dry wind carrying salt crystals across a surface that stretches, flat and featureless, to every compass point. This is the Salar de Atacama, the largest salt flat in Chile, sitting at an elevation of 2,300 meters above sea level in one of the driest places on the surface of the planet. Rainfall here is measured not in centimeters, but in millimeters per decade. The air is so thin and dry that many organisms cannot survive it. And yet, beneath that blinding white crust, something extraordinary has been accumulating for millions of years. A brine, a mineral-rich liquid more concentrated than seawater, more chemically complex than almost any natural water on Earth, sits in vast underground pools, slowly thickening under the relentless evaporation of the Atacama Sun. And dissolved in that brine, in concentrations that make geologists and economists alike grow very still and very attentive, is lithium. To understand how it got there, you have to think in geological time, in millions of years, not thousands. The Andes Mountains are a relatively young range in geological terms, thrown up by the collision of the Nazca tectonic plate with the South American plate over the last 70 million years. As they rose, they trapped moisture from the east, creating the extreme aridity of the Atacama to the west, while feeding a complex system of volcanoes, geothermal zones, and high-altitude basins called salares, salt flats, to the east. Deep beneath these basins, the Earth's heat drives hydrothermal circulation. Groundwater percolates down into hot rock, dissolves minerals from it, including lithium, which is present in trace amounts throughout most continental crust, and then rises back toward the surface as warm, mineral-laden brine. Over millions of years, these brines collect in closed basins where there is no outlet to the sea. The water evaporates, the minerals remain, and the brine grows ever more concentrated. Lithium, being highly soluble and not prone to precipitating out of solution the way calcium or sulfate do, stays in the liquid. It accumulates. It waits. You might ask why lithium is in the rock at all. The answer brings us back to the Big Bang and to the violent history of stars. The lithium in the crust of the Earth arrived here primarily through two routes. Some of it is primordial, the trace amounts of lithium-7 forged in the first 3 minutes of the universe, incorporated into the solar nebula that eventually became our Sun and its planets. Some of it was produced later by cosmic ray spallation, energetic particles from supernovae smashing into carbon and oxygen in the interstellar medium and creating lithium as a byproduct. All of it eventually ended up, through billions of years of accretion and differentiation and volcanic cycling, distributed in tiny concentrations throughout the rocks of the Earth's crust. On average, the crust contains about 20 parts per million of lithium, enough to detect, not enough to be useful. But the hydrothermal systems of the Andes, working patiently over geological time, have done something remarkable. They have taken that diffuse, near-invisible trace element and concentrated it by factors of hundreds or even thousands, pumping it through kilometers of rock and depositing it in these high desert basins like water in a cistern. The result is what miners call a brine deposit, and the Atacama brine is one of the richest lithium deposits anywhere on Earth. When you pump it up, it is not clear. It has a faintly yellowish tinge from the minerals dissolved in it, and it leaves a crust of salt on everything it touches. It does not look like the stuff that powers civilization, but that is exactly what it is. Now here is the perspective shift that I want you to carry with you. Close your eyes for a moment and imagine you are standing on the surface of the Salar de Atacama. The ground is warm under your feet from the sun. The air is utterly still. Beneath you, not far beneath you, perhaps 10 or 15 meters down in places, there are pools of brine that have been accumulating since before the first humans crossed into the Americas. That brine contains, dissolved within it, enough lithium to power electric vehicles for millions of drivers. The lithium that will one day sit inside the battery of a car in Berlin or Boston or Beijing was, until very recently, sitting quietly under the feet of flamingos. Yes, flamingos. Because here is the detail that makes the Atacama feel like a different kind of story entirely. The Salar de Atacama is not a dead landscape. Around the edges of the salt flat, where freshwater streams from the Andes bring nutrients into the system, there are lagoons. And in those lagoons, in shallow water the color of pink champagne from the algae that thrive in it, thousands of Andean flamingos feed. They are pink from the same carotenoids they filter from the brine shrimp and algae of these lagoons. They nest here, on mounds of salt and mud, returning year after year to the same spots they have used for thousands of years. The flamingo colonies of the Atacama are among the largest in the world, and they exist in a precise ecological balance with this extreme environment. An environment that is now, in a matter of decades, being transformed into an industrial landscape. But we are getting ahead of ourselves. Before we get to what is happening now, we need to understand what this landscape meant to the people who lived beside it for centuries before the rest of the world discovered what was hidden beneath it. The Atacameño people, the Licanantay, have inhabited this region for at least 10,000 years. They built an intricate civilization adapted to extreme aridity, developing sophisticated irrigation systems, domesticating llamas, trading across the continent along routes that crossed the Andes at altitudes that would incapacitate an unacclimatized lowlander. They knew the salares. They harvested salt from them. They understood the brine. They observed the flamingos with the attentiveness of people for whom every feature of the landscape has practical meaning. For them, the white desert was not a wasteland waiting to be exploited. It was home. It was sacred. And somewhere in the ground beneath their feet, the ancient tiers of vanished lakes lay waiting, patient as the universe itself, for the moment when the rest of the world would finally understand what they were worth. The Earth kept these deposits for millions of years. It took us approximately 40 years after their discovery to begin depleting them. That discrepancy between geological patience and human urgency is one of the defining tensions of our time. And it begins, as so many modern stories do, with a phone call, a battery, and the quiet desperation of a world running out of options. In the autumn of 1948, a quiet, methodical Australian psychiatrist named John Cade was working in a condition that would strike most modern researchers as somewhere between austere and desperate. He had a small laboratory behind the Bundoora Repatriation Mental Hospital in Victoria, a converted kitchen by most accounts, with minimal funding, no research assistants, and no sophisticated equipment. What he had was a question that had haunted psychiatry for generations. What caused mania? Not depression, not anxiety, not the general fog of mental illness, but that specific, terrifying condition in which a person's mind accelerates beyond all normal limits, thoughts racing faster than speech can follow, grandiosity expanding until the individual is convinced of their own divine importance, energy so relentless that they stop sleeping for days, behaviors so impulsive and unfiltered that they destroy relationships, finances, and sometimes lives in the span of a single week. Cade had a hypothesis, a somewhat eccentric one, as hypotheses that turn out to be correct often are. He believed that mania might be caused by some toxic substance produced in excess by the body and excreted in urine. It sounds almost medieval now, but it was a reasonable inference for the time, and Cade set about testing it in the most direct way he could think of. He injected urine from manic patients into guinea pigs and observed what happened. This is the part of the story where you should feel a complicated mixture of sympathy and admiration for John Cade, because the experiments were exactly as unglamorous as they sound, and the early results were inconclusive. But Cade pressed on. He was trying to identify which component of the urine might be responsible for any toxic effect, and one of the compounds he focused on was uric acid, the same compound whose excess causes gout. When he tried to inject uric acid solutions into his guinea pigs, he ran into a practical problem. Uric acid does not dissolve easily in water. To make it soluble enough to inject, he needed to use one of its salts. The most soluble uric acid salt he had available was lithium urate. So he made lithium urate solutions, injected them into his guinea pigs, and noticed something unexpected. The guinea pigs, rather than becoming more agitated or showing signs of toxicity, became calm. Unusually, almost eerily calm. They remained fully alert and responsive, but the normal skittishness of laboratory guinea pigs, the constant twitching, the readiness to startle, was replaced by a placid, settled demeanor that Cade had not seen in animals receiving other treatments. He realized, with the careful logic of a good experimentalist, that the effect might not be from the uric acid at all. It might be from the lithium. He tested lithium carbonate separately. The calming effect remained. He tried other lithium salts. Same result. The lithium, not the urate, was doing something to the nervous system of these animals. Something real, something measurable, something that had never been systematically documented in the scientific literature. Cade then did something that would be unthinkable under modern research ethics, something that was, even at the time, an act of considerable personal courage and arguably considerable recklessness. He tested the compound on himself first. He took lithium citrate for several weeks, monitoring himself for toxic effects, and when he was satisfied that the doses he intended to use were not immediately dangerous to a human being, he brought his findings to the most severe test he could imagine. He selected 10 patients with severe chronic mania, men who had been hospitalized for years, whose conditions were considered essentially untreatable, who had in some cases been manic almost continuously for years or even decades. He began giving them lithium. The results, published in the Medical Journal of Australia in 1949, in a paper that initially attracted almost no attention, were remarkable. Patient after patient stabilized. The racing thoughts slowed. The grandiosity faded. The exhausting, destructive energy of mania eased into something that resembled, for the first time in years, in some cases, ordinary human affect. Men who had been considered hopeless were sitting calmly, holding conversations, sleeping through the night. One of Cade's earliest patients, a man named William Brand, who had been in a state of almost continuous manic excitement for 5 years, was discharged from the hospital within 2 months of beginning lithium treatment and returned to his previous employment. He remained well for years. Now, and this is where the story takes a turn that reveals something important about how science actually works, as opposed to how we like to imagine it works, the discovery was almost immediately suppressed. Not by a conspiracy, not by malice, but by tragedy. Shortly after Cade's paper appeared, several patients in other facilities who were given lithium developed toxicity. Lithium, it turned out, was a compound with a narrow therapeutic window. The gap between a dose that helps and a dose that harms is unusually small, and in the late 1940s, in hospitals that were already using lithium chloride as a salt substitute for cardiac patients on low-sodium diets, several deaths had occurred from lithium poisoning. The compound was associated in the medical mind with danger. Regulatory agencies in the United States effectively banned its use. John Cade's discovery, one of the most significant in the history of psychiatry, spent nearly 2 decades in obscurity. It was a Danish psychiatrist named Mogens Schou who eventually rescued it, conducting the careful, controlled clinical trials through the 1950s and 60s that demonstrated lithium's efficacy and established the blood level monitoring protocols that made it safe to use. By the 1970s, lithium carbonate was approved by the U.S. Food and Drug Administration, that is, FDA, and it began its quiet transformation into the most important mood-stabilizing medication in the history of medicine. Here is the thing that makes lithium's psychiatric story genuinely strange, and this strangeness has never entirely been resolved. We still do not know exactly how it works. After 75 years of research, after tens of millions of prescriptions filled, after lithium has become the standard against which every other mood stabilizer is measured, the precise molecular mechanism by which a lithium ion slows manic episodes and prevents the cycling between mania and depression in bipolar disorder remains incompletely understood. There are theories, good ones. Lithium appears to inhibit an enzyme called glycogen synthase kinase 3 beta, which plays a role in regulating neuronal activity and the expression of certain genes involved in cell survival and synaptic plasticity. It affects the levels of serotonin and dopamine in the brain. It may protect neurons from the kind of stress-induced damage that accumulates over repeated episodes of mood disturbance. It appears to promote neurogenesis, the growth of new brain cells, in the hippocampus, a region critical for memory and emotional regulation. But none of these explanations is complete, and scientists continue to argue about which mechanism is primary. There is something almost philosophically appropriate about this. Lithium is the third element. It sits at the beginning of everything, and the way it works in the human mind is, like the universe itself, not entirely legible to us. What we know for certain is the clinical reality. For many people with bipolar disorder, lithium is the difference between a life of catastrophic oscillation and a life of functional stability. It reduces the risk of suicide in bipolar patients more effectively than almost any other psychiatric medication, and that is not a minor statistic, because bipolar disorder carries one of the highest suicide rates of any psychiatric condition. There are people alive today living ordinary lives, raising children, going to work, who would almost certainly not be here if John Cade had not turned to lithium urate to solve a solubility problem in a converted kitchen in Melbourne in 1948. And yet the same properties that make lithium valuable in medicine, its chemical eagerness, its willingness to interfere with biological systems, also make it genuinely dangerous. The therapeutic blood level for lithium is between 0.6 and 1.2 millimoles per liter. Toxic effects begin to appear at levels above 1.5. At 2 or above, a patient may experience severe tremors, confusion, and kidney damage. Higher still, and the consequences can be life-threatening. This means that every patient on lithium must have their blood levels monitored regularly, must be careful about dehydration, must be aware that something as ordinary as a summer illness with vomiting can push their lithium levels into dangerous territory. The line between the dose that calms the storm and the dose that creates a different kind of crisis is measured in decimal points. A metal so reactive it attacks air. A medication so precise it is measured in fractions. A therapy so powerful it saved millions of lives. And so delicate it can become its own threat. This is lithium's double nature, and it runs through every chapter of its story like a thread of crimson fire. There are moments in the history of physics when the math leads somewhere that the physicists themselves are not entirely comfortable going. The late 1930s and early 1940s were full of such moments, and the discomfort was entirely justified. Because the place the math was leading was toward the liberation of energies that had been locked inside atomic nuclei since the beginning of time. By the time the Second World War ended in 1945, 2 cities had demonstrated what fission, the splitting of heavy atomic nuclei, could do at its most terrible. But even as the rubble was still being cataloged, physicists in the United States, the Soviet Union, and Britain were already thinking about something potentially far more powerful. Fission releases energy by breaking apart the heaviest atoms. Fusion releases energy by forcing the lightest atoms together. The sun runs on fusion. 4 hydrogen nuclei fusing into 1 helium nucleus, releasing the light and heat that makes life on Earth possible. In a controlled laboratory setting, fusion is extraordinarily difficult to achieve. But in an uncontrolled setting, in the center of a fission explosion, where temperatures of tens of millions of degrees can be reached in microseconds, fusion becomes entirely possible. The question was, what to fuse? Hydrogen isotopes were the obvious answer. Specifically, deuterium and tritium, the heavy forms of hydrogen. A fission bomb could, in theory, be used as a trigger to ignite a fusion reaction, and the resulting explosion would be orders of magnitude more powerful than any pure fission device. The concept was called the thermonuclear bomb, or the hydrogen bomb, and the problem of how to actually build one occupied some of the most brilliant minds of the 20th century for nearly a decade. Lithium entered this story not as the primary fuel, but as a solution to a critical engineering problem. Tritium, the heaviest isotope of hydrogen with 1 proton and 2 neutrons, is radioactive and extraordinarily rare. Producing it in the quantities needed for a weapon would require either enormous quantities of reactor space or some alternative approach. The alternative turned out to involve lithium. Specifically, the isotope lithium-6. When lithium-6 is struck by a neutron, it undergoes a reaction. It absorbs the neutron and splits into a helium nucleus and a tritium nucleus. In other words, if you pack lithium-6 into a thermonuclear device alongside deuterium, the fission trigger produces neutrons. Those neutrons hit the lithium-6 and generate tritium on the spot. And the tritium immediately fuses with the deuterium in a chain of reactions that releases staggering amounts of energy. The lithium-6 does not just sit there passively. It participates. It manufactures its own fuel mid-explosion. This insight, credited in various forms to Edward Teller, Stanislaw Ulam, and a team of researchers at Los Alamos, was the conceptual breakthrough that made practical thermonuclear weapons possible. The fuel was not liquid hydrogen, difficult to store and handle, but lithium deuteride, a solid, salt-like compound, stable at room temperature, easy to machine into the precise shapes required by the weapon's design. You could hold it in your hand. It looked unremarkable. And it was, gram for gram, the most energetically dense material ever placed in a human weapon. The first full-scale test of this design came on March 1, 1954, at Bikini Atoll in the Marshall Islands. The test was codenamed Castle Bravo, and it was intended to yield approximately 5 megatons, 5 million tons of TNT equivalent. That was already an almost incomprehensible figure, roughly 350 times the yield of the bomb that destroyed Hiroshima. The actual yield was 15 megatons, nearly 3 times the predicted value. The weapon had detonated with an energy release that no one had calculated and no one had fully anticipated, and it instantly became the largest nuclear explosion ever set off by the United States. What went wrong? Or rather, what the designers had failed to account for, brings us back to lithium in a way that reveals something important about how even the most sophisticated scientific calculations can contain hidden assumptions that turn out to be critically wrong. The lithium deuteride in Castle Bravo was made from natural lithium, which contains approximately 7.5% lithium-6 and 92.5% lithium-7. The weapon designers had accounted for the lithium-6 contribution carefully. What they had not fully accounted for was the behavior of lithium-7. The standard assumption at the time was that lithium-7 was essentially inert in the context of the explosion, that it would absorb neutrons without contributing significantly to the fusion fuel production. This assumption was wrong. Under the extreme conditions inside the exploding weapon, lithium-7 proved capable of reacting with fast neutrons to produce tritium as well. Not as efficiently as lithium-6, but efficiently enough when you have 92% of your lithium in that form to dramatically increase the tritium available for fusion. The yield tripled. The fallout cloud spread across an area far larger than planned, dusting the crew of a nearby Japanese fishing vessel called the Lucky Dragon No. 5 with radioactive ash. One crew member later died from radiation-related illness. Residents of the Marshall Islands were exposed to significant fallout, with health consequences that continued for decades. Castle Bravo changed the calculus of the nuclear age in ways that reverberate to this day. It demonstrated that thermonuclear weapons could be made arbitrarily large, that there was no obvious upper limit to the destructive yield achievable by stacking lithium deuteride around a fission trigger. It accelerated the nuclear arms race. It contributed to the eventual push for atmospheric test ban treaties. And it did all of this, at least in part, because a small isotope of lithium behaved differently than anyone had expected under conditions no one had ever experienced before. Stand back from the details for a moment and let the full picture resolve. The same element forged in the Big Bang, the same element that drifts in the brines beneath the Atacama, the same element that John Cade had used just 5 years earlier to bring peace to suffering minds. This element, in a slightly different isotopic form, had become the key component of the most destructive device ever built. The flame that lit the universe, recreated by human hands. Not to illuminate, not to warm, to erase. There is a particular kind of horror in that symmetry that no amount of clinical language can fully dissolve. And there is something else, something that the physicists who built these weapons understood, even as they built them. Fusion, the very process that thermonuclear weapons exploit, is also the process that could, in principle, provide humanity with unlimited clean energy. The same lithium, the same physics. The difference between the sword and the sun is only a matter of how you arrange the geometry, how you control the reaction, how you choose to direct the fire. Lithium, element number 3, born at the beginning of time, it has never cared which way we point it. That has always been our choice, and ours alone. Let us talk about what is happening in your pocket right now. Not metaphorically, literally, right now, as you listen to these words. If you are holding a smartphone, or if one is sitting within arm's reach, there is a battery inside it. That battery contains a thin layer of graphite, the same carbon material used in pencil leads, on one side, and a lithium metal oxide compound on the other side. Between them is a liquid electrolyte, a chemical medium through which ions can travel. And at this very moment, if your phone is in use, millions upon millions of lithium ions are migrating through that electrolyte from the graphite side toward the metal oxide side, each one releasing a tiny electrical charge as it moves, the cumulative flow of all those charges powering the processor, the screen, the radio transmitter that connects you to the rest of the world. If you then plug your phone into a charger, the process reverses. Electricity from the wall pushes those lithium ions back across the electrolyte, parking them once again in the graphite structure, ready to make the journey again. This cycle, which your phone's battery performs hundreds of times across its working life, is called intercalation. The lithium ions do not react chemically with the electrode materials in the way that, say, lithium reacts with water. They simply slip between the layers of the crystal structure, like pages being shuffled into a book and then removed again, without permanently altering the electrode. That is the elegance of the lithium-ion battery. That is why it can be charged and discharged so many times without catastrophic degradation. But to understand why this particular chemistry came to dominate the modern world, you have to go back to the 1970s, to a moment of global crisis, and to a scientist who was thinking about physics in a way that nobody else quite was. The year is 1973. The Arab members of the Organization of Petroleum Exporting Countries, OPEC, announce an oil embargo against nations that supported Israel in the Yom Kippur War. The price of oil quadruples almost overnight. In the United States, drivers queue for hours at gas stations. Heating oil becomes scarce. The economy shudders. And in research laboratories, a new urgency crystallizes around a question that had previously been considered academic. Could electricity be stored efficiently in a small, light, rechargeable package? The batteries that existed in the early 1970s were not promising candidates. Lead-acid batteries, the kind still used to start internal combustion engines, were heavy, large, and could not be miniaturized meaningfully. Nickel-cadmium batteries were better, but still heavy and plagued by the so-called memory effect, which caused them to lose capacity if not fully discharged before recharging. Neither was going to power a portable future. Stanley Whittingham was a British chemist working at Exxon. Yes, the oil company, which in the 1970s was hedging its bets about the energy future with a genuine research program in alternative technologies. He was studying a class of materials called layered chalcogenides, and he noticed that titanium disulfide had a remarkable property. It could accept lithium ions between its layers and release them again without falling apart. He built a prototype battery using a titanium disulfide cathode and a lithium metal anode, and it worked. It was rechargeable, it was reasonably energetic, and it demonstrated a concept that would eventually change the world. But there was a problem, and it was a serious one. Pure lithium metal as the anode is not safe. When you charge a lithium metal battery repeatedly, tiny needle-like structures called dendrites grow from the lithium surface. These dendrites can eventually puncture the separator between the anode and cathode, causing a short circuit that can result in fire or explosion. Whittingham's batteries were promising, but dangerous, and Exxon eventually shelved the research program as oil prices stabilized and the urgency of the 1970s faded. The baton passed to John Goodenough, a name that sounds almost too appropriate for a man whose contributions to the modern world can scarcely be overstated. Goodenough, working at Oxford in the early 1980s, was studying transition metal oxides and their ability to intercalate lithium ions. He discovered that lithium cobalt oxide could serve as a cathode material with a higher voltage than Whittingham's titanium disulfide, meaning more energy could be stored in the same amount of material. He published his findings, making them freely available rather than patenting them, in what he has described as a deliberate choice to ensure the technology could be developed by anyone. He was in his late 50s at the time. He would go on to make further foundational contributions to battery science well into his 90s. In 2019, at the age of 97, he was awarded the Nobel Prize in Chemistry, the oldest person ever to receive the honor. The third piece of the puzzle was provided by Akira Yoshino, a Japanese chemist at the Asahi Kasei Corporation, who in 1985 made the critical substitution that made lithium-ion batteries commercially viable and safe. He replaced the dangerous pure lithium metal anode with petroleum coke, a carbon material in which lithium ions could be safely stored. No more dendrites, no more explosion risk from cycling. The battery could be charged and discharged hundreds of times without catastrophic failure. Yoshino's design was the direct ancestor of every lithium-ion battery manufactured today. Sony commercialized the first lithium-ion battery in 1991. Within a decade, it had revolutionized portable electronics. Within 2 decades, it had made the smartphone possible. Within 3 decades, it was transforming the automotive industry. The numbers involved are staggering. In 2023, humanity manufactured approximately 800 gigawatt-hours of lithium-ion battery capacity, a figure that would have seemed like science fiction to Whittingham sitting in his Exxon laboratory in 1973. Each electric vehicle on the road today contains somewhere between 40 and 100 kilowatt-hours of battery capacity. Each battery pack contains somewhere between 6 and 12 kilograms of lithium. Multiply those numbers by the tens of millions of electric vehicles currently in operation and the hundreds of millions projected for the coming decades, and the scale of the lithium demand becomes almost vertiginous. But here is the detail that I want you to carry with you, because it transforms the abstraction into something immediate and personal. The lithium in your phone's battery, perhaps 2 or 3 grams of it, began its journey in the brine beneath a South American salt flat, or in a hard rock deposit in Australia, or in a clay formation in Nevada. It was extracted, refined, processed through multiple chemical transformations, shipped across oceans, incorporated into electrode materials by machines in factories in China or South Korea or Japan, assembled into the battery cell that was then built into the device you are now holding. Every step of that journey consumed energy and water and human labor. The battery represents, in a form factor smaller than a paperback book, an almost incomprehensible coordination of global resources and industrial capability. And it enables you to carry, in your pocket, more computing power than existed in the entire world in 1970. The Sleeping Djinn, as the old stories have it, is the most powerful creature imaginable, but only when awakened, only when the right words are spoken, only when the conditions are precisely right. Lithium is exactly that. Dormant in the brine, dormant in the rock, dormant in the oxide structure of a cathode. And then, when the circuit closes, when the electrons need somewhere to go, the ions begin their quiet, relentless migration, and the energy flows. Silently, without combustion, without smoke. Billions of times per second, in billions of devices, on every continent on Earth. The Djinn is awake. The question now is whether we have the wisdom to be worthy of what we have awakened. The photographs from above look almost abstract, great parallelograms of vivid color laid across the white expanse of the Atacama salt flat like a geometric painting. There are greens and yellows and pale blues, arranged in neat rectangular pools that stretch for kilometers, their edges precise and engineered against the wild chaos of the surrounding desert. These are the evaporation ponds of a lithium mining operation, and they are among the most surreal industrial landscapes on the surface of the planet. Brine pumped from deep below the salt crust is channeled into these pools, and then the Atacama does what it does better than almost anywhere else on Earth. It evaporates the water. Over the course of 12 to 18 months, the brine moves through a sequence of ponds, growing more concentrated with each transfer as water leaves and minerals remain. First, the halite, common salt, precipitates out. Then the potassium compounds. By the end of the process, a lithium-rich solution remains, ready for further chemical processing. This method is called solar evaporation, and it is cheap and effective, and it has a problem. The brines of the Atacama do not exist in isolation. They are part of a hydrological system, a system that connects the underground aquifers to the surface lagoons, to the streams that flow down from the Andes, to the wetlands where flamingos nest. When you pump brine from deep underground, you change the pressure in the aquifer. When you change the pressure, you alter the flow of water through the system. And when you alter the flow of water in one of the driest ecosystems on Earth, the consequences cascade in ways that are difficult to predict and, once set in motion, difficult to reverse. The Licanantai communities of the Atacama have been watching this cascade for 3 decades. The wetlands they call Vegas and Bofedales, high-altitude marshes fed by underground springs, are drying. Water sources that their grandparents relied on are diminishing. The flamingo populations in some lagoons are declining. The quinoa they grow in fields irrigated by channels that have functioned since pre-Columbian times is under stress. And the process is accelerating.
because the world's appetite for lithium is accelerating. In 2022, global lithium production was approximately 130,000 metric tons. By 2030, projections suggest demand could reach 3 to 4 times that figure, driven by the electric vehicle transition, by grid-scale energy storage, by the expansion of consumer electronics into every corner of the global economy. Every percentage point increase in electric vehicle adoption translates, somewhere in the Atacama or in Bolivia's Salar de Uyuni or in Argentina's Salar del Hombre Muerto, into more brine pumped, more water evaporated, more pressure on the hydrological systems that indigenous communities and flamingo colonies alike depend on. Now for the cruelest irony in this entire story, and in a story as rich with irony as lithium's, that is saying something. The electric vehicle revolution is driven by climate change. The imperative to replace gasoline engines with battery-powered alternatives exists because burning fossil fuels is warming the planet, shifting precipitation patterns, intensifying droughts, threatening ecosystems. The cure, in the Atacama, looks disturbingly like a new version of the disease. We are drying out wetlands and depleting indigenous water sources to produce the batteries that we hope will stop us from drying out wetlands and depleting water sources globally. The people who are paying the immediate price for the green transition are not the people who will drive the electric vehicles. They are the Licananti families whose springs are going quiet, whose flamingos are leaving, whose land is being transformed at a speed that 10,000 years of careful coexistence did not prepare them for. The geopolitics of this transformation have their own texture of drama. The so-called Lithium Triangle, the region encompassing the Atacama deposits of Chile and Argentina, along with the vast salt flat of Salar de Uyuni in Bolivia, holds an estimated 50 to 60% of the world's known lithium reserves. This concentration of a strategic resource in a single geographic region has drawn the attention of governments and corporations with the same hungry intensity that Middle Eastern oil fields once commanded. China, through its companies and state investment vehicles, has moved aggressively to secure lithium supply chains, acquiring stakes in mines, processing facilities, and battery manufacturers across the Lithium Triangle and beyond. The United States, recognizing the strategic vulnerability of depending on adversary nations for materials critical to both its clean energy transition and its defense industries, has classified lithium as a critical mineral and begun subsidizing domestic production and processing. The European Union has done the same. Bolivia, sitting atop what may be the world's single largest lithium deposit in the Salar de Uyuni, has spent years attempting to develop a state-owned lithium industry that would keep the profits within its borders rather than exporting them to multinational corporations. A politically understandable position that has also meant slower development and more complex negotiations with the foreign companies that possess the technology and capital to extract and process the resource efficiently. The competition for control over lithium supply is not merely economic. It is military, diplomatic, and existential in the sense that whoever controls the batteries controls the electric vehicles, and whoever controls the electric vehicles controls a significant portion of the transportation infrastructure of the 21st century. A technology company or a nation that cannot secure reliable lithium supplies faces a fundamental constraint on its ability to compete in the energy economy that is taking shape around us. This is not hypothetical. It is happening now, in boardrooms and foreign ministries and rural communities in the Andes, every day. There is a technology that promises to change this equation, or at least to complicate it productively. Direct lithium extraction, DLE, is a family of technologies that, rather than pumping brine into ponds and waiting 18 months for the sun to concentrate it, passes the brine through selective adsorbents or membranes that pull out the lithium ions directly, with far less water consumption and in a fraction of the time. Pilot plants are operating in several locations, and multiple companies have announced plans to commercialize the technology at scale within the next few years. If DLE works as its proponents promise, if it can extract lithium efficiently from lower-grade brines, from geothermal waters, even from seawater, it could simultaneously reduce the environmental footprint of lithium production, increase the global supply, and make the resource geography less concentrated. It could also, in theory, be deployed in locations that currently lack viable lithium deposits,
using brine from geothermal operations, from oil field-produced water, from desalination plants. The lithium in seawater alone, if it could be economically extracted, would be effectively inexhaustible. But DLE remains expensive and unproven at full commercial scale. The evaporation ponds are still being built. The brine is still being pumped. And every day, the white desert of the Atacama is being asked to give up a little more of what took millions of years to accumulate. We are spending in decades what the Earth saved across geological ages. We are drinking the water of the past to power the energy of the future. And somewhere in the middle of that transaction, between the dried spring and the charged battery, between the flamingo's empty lagoon and the silent electric vehicle moving down a city street, there is a moral account that has not yet been settled, and that grows more complex with every ton of lithium we pull from the ground. There is a county in western Texas called Crane County. It sits in the Permian Basin, a landscape of scrub brush and pump jacks and enormous skies that most people drive through without stopping. The population is small. The economy runs on oil. It is not the kind of place that comes up in conversations about mental health research. And yet, in the early 2000s, a psychiatrist named Gerhard Schrauzer and a team of researchers examined the public health data from Texas counties and found something in Crane County and its neighbors that they could not immediately explain. The rates of certain violent and impulsive behaviors, arrests, hospitalizations following self-harm episodes, a cluster of outcomes associated with severe mood dysregulation, were statistically lower in some counties than in others. The researchers began looking for what might account for the variation. They controlled for income, for population density, for access to healthcare, for demographic differences. The correlations shifted but did not disappear. Then someone looked at the water. Specifically, someone looked at the lithium content of the public water supply in different Texas counties. And what they found was a correlation that has since been replicated, with varying degrees of strength and consistency, in studies conducted in Japan, in Greece, in Austria, in Lithuania, which is, it must be noted, a country whose name is purely coincidental to all of this, but which provides a certain narrative satisfaction. In regions where the drinking water naturally contains higher concentrations of lithium, still far below any therapeutic dose, in the range of micrograms per liter rather than the milligrams per liter used in psychiatric treatment, certain population-level indicators of mental health and social stability appear, on average, to be somewhat better. The association is most consistently reported for suicide rates. A study published in the British Journal of Psychiatry, examining 27 municipalities in Oita Prefecture in Japan, found that areas with higher natural lithium in drinking water had statistically lower suicide rates, even after controlling for other variables. A large Austrian study published in 2013 found similar patterns. A study in Greece, in the United Kingdom, in several other countries. The picture that emerges, while not perfectly consistent across every dataset, points in the same direction often enough to demand attention. Now, here is where the science becomes genuinely difficult and genuinely fascinating, because correlation in epidemiology is both the beginning of discovery and a notorious source of error. The history of public health is full of associations that turned out to be confounded, cases where two variables track together not because one caused the other, but because both were driven by some third factor that nobody initially thought to measure. So when researchers find that counties with more lithium in the water have lower suicide rates, the obvious and necessary question is the lithium actually doing something to the brains of the people drinking it, or is there some other feature of the geology, the economy, the culture, or the demographics of high lithium regions that explains the pattern? Some researchers have argued that the lithium in drinking water, even at microgram concentrations, is genuinely pharmacologically active at the population level, that chronic, low-level exposure to lithium ions could have subtle stabilizing effects on neuronal signaling, similar in kind, if not in magnitude, to the effects of therapeutic doses. They point to animal studies in which rodents given water supplemented with trace amounts of lithium show reduced aggression and altered behavior. They point to the fact that lithium's pharmacological effects on the brain are not fully understood at any dose level, which makes it plausible that low-dose effects exist even if they cannot yet be precisely characterized. Others are deeply skeptical. The epidemiological associations, they argue, are weak and inconsistent across datasets.
The confounding variables in population-level studies are numerous and difficult to fully control. The gap between microgram and milligram concentrations spans multiple orders of magnitude, and there is no established mechanism by which doses this small could produce meaningful neurological effects. Without a randomized controlled trial, which would be extraordinarily difficult to design and conduct ethically, the question cannot be definitively answered. And so the mystery sits, unresolved. Quietly provocative. Think about what it would mean if the association were real. If lithium, seeping naturally through geological formations into aquifers and from there into tap water, were acting as an invisible, inadvertent mood modulator for entire populations. It would mean that the mental health of communities is shaped, at least in part, by the chemical composition of the ground beneath them. It would mean that two cities built side by side on different geological substrates could have meaningfully different rates of suicide and impulsive violence, not because of any social or economic factor, but because of the lithium content of their bedrock. It would mean that the history of certain cultures, their characteristic temperaments, their rates of certain disorders, the social behaviors that anthropologists and historians have attributed to religion and economics and climate, could have been influenced, in ways we have never suspected, by the quiet chemistry of their water supply. Some researchers have taken to calling this the invisible psychiatrist hypothesis. Others use the phrase lithium as a natural mood stabilizer for populations. The metaphor of pollen, of something carried invisibly through the environment, touching everyone it reaches, shaping the biochemistry of communities without their knowledge or consent, captures something important about why this idea is simultaneously fascinating and unsettling. Because if it is true, it raises questions that have no clean answers. Should lithium be added to public drinking water deliberately, the way fluoride is added to prevent tooth decay? This suggestion has been made seriously in the scientific literature, and it has been met with a reaction that ranges from cautious interest to outright alarm. The history of fluoridation itself, a scientifically sound public health intervention that nonetheless became a focal point for public distrust of government and institutional authority, suggests that even if the evidence for lithium in water were overwhelming, the path to any kind of policy intervention would be extraordinarily complex. And the evidence, as we have established, is not yet overwhelming. It is suggestive. It is intriguing. It is the kind of evidence that makes careful scientists say we need more data, while a certain kind of headline writer reaches for words like miracle mineral and the government's secret mood drug. The reality is more interesting than either of those framings. What the lithium in water research actually reveals is something profound about the relationship between geology and human consciousness, about the degree to which the minds that built civilization were themselves built, in part, by the earth those civilizations stood on. We think of mental health as something that happens inside individuals, shaped by genetics and childhood and trauma and choice. And it is all of those things, but it is also, possibly, shaped by the mineral content of the rain that falls on the mountains above your city and filters through limestone or granite or volcanic rock before it reaches your glass. Element number 3, forged in the Big Bang, concentrated in ancient brines, discovered in a crimson flame in Brazil, used to build the most destructive weapons ever conceived, and now potentially whispering its chemistry into the nervous systems of millions of people through the simple, daily act of drinking water. There is no clean moral to this discovery. There is only the strange, vertiginous sensation of realizing that the world is more chemically intimate than you had imagined, that the stone beneath your feet is not inert, that it has, perhaps, been talking to your brain all along. In the south of France, about 60 kilometers north of Marseille, in a landscape of lavender fields and limestone hills, and the particular golden light that has made Provence famous for centuries, there is a construction site unlike any other on the surface of the earth. It does not look extraordinary from the outside. There are cranes and concrete and the organized chaos of heavy industrial construction, the kind of scene you might find at any large infrastructure project anywhere in the world. But inside the growing complex of buildings, at the center of a structure that will eventually be the size of a large sports arena, something is being assembled that has no precedent in the history of human engineering. A machine designed to contain a star. Not metaphorically, not approximately. A machine designed to recreate, inside a vacuum vessel roughly 11 meters across, the conditions that exist at the core of our sun. Temperatures exceeding 150 million degrees Celsius, 10 times hotter than the sun's own core. Hot enough for hydrogen isotopes to fuse and release the energy that has powered every star in the universe since the beginning of time. The project is called ITER, International Thermonuclear Experimental Reactor, and it represents the largest scientific collaboration in human history. 35 nations are contributing to its construction and funding, including the United States, the European Union, China, Russia, India, Japan, and South Korea. The machine is called a tokamak, a word derived from a Russian acronym for toroidal chamber with magnetic coils, and it uses superconducting magnets of extraordinary power to confine a plasma of hydrogen isotopes in a donut-shaped magnetic field, preventing the 150 million degree plasma from touching the walls of the vessel and cooling down. If it works as designed, ITER will produce 10 times more energy than it consumes, a milestone that no fusion experiment has ever achieved. And at the center of how it works, woven into its design in multiple critical ways, is lithium. The fusion reaction that ITER is designed to sustain uses two isotopes of hydrogen, deuterium and tritium. Deuterium is abundant. It can be extracted from ordinary seawater, where it constitutes about 1 in every 6,000 hydrogen atoms. Tritium is another matter. Tritium is radioactive, with a half-life of about 12 years, and it does not occur naturally in significant quantities. It must be produced. The solution that fusion engineers have developed, and which ITER is partially designed to test, involves lithium. Around the plasma vessel, in the region called the breeding blanket, lithium-bearing material will absorb the high-energy neutrons produced by the fusion reaction. When lithium-6 absorbs a neutron, it produces tritium and helium. When lithium-7 absorbs a very energetic neutron, it also produces tritium, along with a spare neutron that can breed more tritium from more lithium. In this way, the reactor breeds its own fuel. It begins with an initial charge of tritium, sustains the fusion reaction, and uses the neutrons produced by that reaction to manufacture more tritium from its lithium blanket. If the blanket is designed correctly, if the lithium loading, the geometry, the neutron moderators, and the tritium extraction systems all work together as planned, the reactor can sustain itself on a trickle of external tritium supply while breeding everything else it needs. This is the closed loop that makes fusion power potentially so attractive. The fuel cycle, in its simplest form, goes like this. Seawater provides deuterium, lithium provides the material to breed tritium, and the fusion of deuterium and tritium releases enormous amounts of energy with no carbon dioxide, no long-lived radioactive waste of the kind produced by conventional fission reactors, and no possibility of a runaway chain reaction. The fundamental physics does not allow a fusion reactor to explode the way a fission reactor can melt down. If you lose confinement, the plasma simply cools and the reaction stops. And the fuel supply, for all practical purposes, is inexhaustible. The lithium in seawater alone, even without mining a single salt flat, could power human civilization at current consumption levels for millions of years. Take a moment with that figure. Millions of years. Not decades, not centuries. The scale difference between what we are currently doing with lithium, scraping it from brine ponds in the Atacama, fighting over it in diplomatic chambers, building batteries that last a few years before being discarded, and what fusion power would make possible is almost too large to hold in mind. The dried lagoons, the threatened flamingos, the geopolitical competition over the lithium triangle, all of that exists in a world where we have not yet unlocked what lithium could actually offer. The irony is acute. We are mining the ingredient for the ultimate energy solution in order to power an intermediate energy solution, under pressures that are damaging the very ecosystems we are trying to protect. ITER is scheduled to begin plasma operations in the early 2030s. It will not generate electricity. It is a research device designed to demonstrate scientific and engineering feasibility, not to power a grid. The step after ITER is a demonstration reactor called DEMO,
a project that multiple national programs are pursuing in parallel. DEMO is intended to demonstrate the ability to generate electricity from fusion on a commercial scale. If everything goes according to the most optimistic projections, a qualification that must be applied with some care, given that fusion energy has famously been 30 years away for about 70 years, commercial fusion power could begin to become available sometime in the second half of this century. That timeline is not comfortable. The climate crisis is unfolding on a timescale that does not wait for commercial fusion. The electric vehicle transition and the grid-scale battery storage expansion are happening now with the technology we have, which means the pressure on lithium supplies from mining will intensify for at least the next several decades, regardless of what happens at ITER. But the possibility, the genuine, scientifically credible, engineering plausible possibility that the same element whose scarcity is currently a geopolitical flashpoint could eventually be the medium through which humanity accesses effectively limitless energy, changes the moral and strategic calculus in important ways. The sword, in the ancient story, can be beaten into a plowshare. The weapon can become a tool. The destructive fire, patiently and skillfully managed, can become the hearth. Castle Bravo demonstrated that human beings can recreate the fusion fire of the first 3 minutes of the universe. ITER is asking whether we can do it gently, whether we can hold the sun in a magnetic bottle and let it warm us rather than burn us, whether the element forged at the dawn of time, the element number 3, the first solid thing that ever was, can be the key that finally opens the door to energy abundance without the shadow of scarcity. That question does not have an answer yet. But the fact that we are asking it in Provence, with 35 nations working together, with magnets cooled to temperatures colder than outer space surrounding a plasma hotter than the sun's core, that fact alone is one of the most remarkable things the human species has ever done. And somewhere in the middle of that extraordinary machine, lithium waits, patient as it has always been, patient as the ancient brines, patient as the universe itself, which made this element in 3 minutes and then spent 13 billion years waiting to see what we would do with it. Here is something I want you to do right now, wherever you are listening to this. If you have a phone in your hand, or a laptop nearby, or headphones in your ears, any device at all that runs on a rechargeable battery, I want you to think about it differently for just a moment. Not as a consumer product, not as a piece of technology, as the end point of a supply chain that begins in the Atacama Desert, passes through a refinery in China, moves through a battery factory in South Korea, crosses an ocean in a shipping container, and arrives, after involving the labor of thousands of people on multiple continents, in your hand. And then, when that battery reaches the end of its useful life, when its capacity has degraded enough that the device no longer holds a charge for long enough to be useful, what happens to it? In the ideal world, the answer is, it gets recycled. The lithium, the cobalt, the nickel, the manganese, all the valuable materials inside the battery are recovered and reprocessed into new battery materials, reducing the need for new mining and closing the loop of the supply chain into something approaching a circle. In the actual world, the answer is far more complicated and considerably less satisfying. Battery recycling rates vary enormously by region and by battery type. Consumer electronics batteries, the small cells in phones and laptops, are recycled at disappointingly low rates in most countries. In the United States, estimates suggest that fewer than 5% of lithium-ion batteries from consumer electronics are properly recycled. In the European Union, regulations have driven recycling rates somewhat higher, and newer legislation is pushing harder still. But the infrastructure to collect, sort, and process end-of-life batteries at the scale that the coming decades will require simply does not yet exist at anything like the necessary scale. This matters enormously because the batteries that are being manufactured today, and the far larger number that will be manufactured over the next 20 years as the electric vehicle fleet expands, will begin reaching end of life in large numbers starting in the late 2030s. A wave of spent battery material is building behind the dam of current production, and if the recycling infrastructure is not built before it arrives, the consequences will be significant. Improper disposal of lithium-ion batteries creates genuine environmental hazards. Lithium itself is not the most toxic component. That distinction belongs to cobalt and nickel, heavy metals that can leach into soil and groundwater if batteries end up in landfills. But lithium-ion cells also carry fire risk during improper handling and processing, and the organic electrolyte solvents inside them are environmentally persistent if released. The image of a green technology revolution built on a foundation of toxic electronic waste is not an abstract concern. It is a documented present reality in regions of West Africa and Southeast Asia, where informal electronics recycling, carried out by hand without protective equipment, using acid baths and open burning to recover metals, is a significant industry. The human and environmental cost of informal recycling is severe, and it falls almost entirely on communities in the global South who did not make the decisions that produced the waste. Zoom out from the battery to the electric vehicle, and the calculation becomes more complex still. The electric vehicle is, in most contexts and over its full life cycle, genuinely better for the climate than the gasoline vehicle it replaces. Lower lifetime emissions, even accounting for the emissions involved in battery production and the current grid mix. That is not in serious scientific dispute. But the claim that electric vehicles are simply clean, simply green, simply the solution, that claim papers over a set of compromises and displacements that deserve honest examination. The cobalt in many lithium-ion battery cathodes comes substantially from the Democratic Republic of Congo, where mining conditions, particularly in the artisanal mining sector, have been documented to involve serious human rights concerns, including the use of child labor. The graphite in battery anodes comes largely from China, produced under environmental conditions that have historically been poor. The lithium comes from the drying wetlands of the Atacama or from hard rock mines in Australia that scar the landscape in their own ways. The transition to electric vehicles is necessary. The physics of climate change leaves us very little choice about that. But necessity does not make something without cost, and the rhetorical habit of describing the electric vehicle as simply clean or simply sustainable obscures the real and ongoing costs being paid by specific communities in specific places. Prometheus stole fire from the gods and gave it to humanity, and the gift was genuine and transformative. It enabled warmth and cooking and metallurgy and every technology that followed. But Prometheus was chained to a rock for his theft, his liver eaten each day and regenerated each night, an eternal consequence for an act of extraordinary audacity. The myth does not end with the gift. It includes the price. We are in the gift phase of the lithium story. We have received the fire, the energy density, the portability, the clean, combustion-free electricity. We are building the electric future on the back of this remarkable element. And the genuine goods of that transition are real. Cleaner air in cities, lower carbon emissions, the possibility of a transportation system that does not depend on burning ancient organisms pulled from the ground. But we have not fully reckoned with the chain. With the Likanantai springs going dry, with the spent batteries piling up in inadequately equipped recycling facilities, with the cobalt supply chain's human costs, with the question of whether there is enough lithium, cobalt, and nickel in accessible deposits to build the battery fleet that a fully electrified global economy would require, or whether the transition will be limited, unevenly distributed, available to wealthy nations while poorer ones are left behind. Some researchers have estimated that if the entire global vehicle fleet were converted to electric vehicles using current battery chemistry, the required lithium supply would exceed all known reserves several times over. This is disputed. Reserves are not a fixed ceiling because higher prices drive exploration and extraction of deposits that are currently uneconomical, and because new battery chemistries that use less lithium or no lithium at all are under active development. Sodium-ion batteries, for instance, use the far more abundant sodium in place of lithium, and while they currently lag in energy density, the gap is narrowing. Solid-state batteries promise greater energy density with potentially smaller amounts of active material. The recycling infrastructure, if built properly, could eventually recover most of the lithium in circulation, making the primary mining requirement a fraction of what current linear supply chain thinking would suggest. The future is not fixed. The constraints are real, but not absolute. And this is, perhaps, the most important thing to understand about where we stand with lithium at this moment in history. We are at the beginning of a transition, not at its end. The decisions being made now about which battery chemistries to develop, which mining practices to permit, which recycling infrastructure to build, which communities to compensate for the costs they are bearing, will determine what the middle and end of this century look like. The element does not make those decisions. It has no preference about how it is used, no stake in the outcome. It simply is what it is, the third element, older than the Earth, forged in the first fire, deposited patiently across geological time, now caught up in the urgency of human history at one of its most consequential inflection points. We hold the fire. The question that Prometheus could not answer, that no myth has ever fully answered, is what kind of people we choose to be while we hold it. 3 minutes. That is how long it took. 3 minutes after the Big Bang for the universe to make the lithium that is now in your phone, in the salt flats of the Atacama, in the neurons of people whose lives are made livable by a tiny white tablet taken each morning with a glass of water. 3 minutes, and then 13.8 billion years of waiting. We have traveled a long way together through this story, from the primordial fire to the research lab, from a converted kitchen in Melbourne to the lavender fields of Provence, from the white silence of the Atacama to the geometric precision of an evaporation pond seen from above. Lithium has appeared in every chapter of the story, not as a supporting character, but as the thread that connects them all. The same atoms, the same element, carrying the imprint of the first moment of time through every transformation the universe has thrown at it. Think about what that actually means. The lithium atoms in the battery of the device you are using right now were forged in the Big Bang. They have existed, in one chemical form or another, for nearly 14 billion years. They were part of the nebula that became the solar system. They settled into the rock of the young Earth. They dissolved into ancient waters. They were concentrated by hydrothermal systems, preserved in underground brines, extracted by industrial machinery, refined and processed and synthesized into electrode material, and assembled into a battery that now sits in a device that you carry in your pocket without giving it a second thought. Every time you charge your phone, you are participating in a chain of events that began at the origin of the universe. There is no way to make that less extraordinary, no matter how mundane the act of plugging in a charger feels. And yet, the story is not only one of wonder, it is also one of consequence. The same element that connected us to the beginning of time has also connected us to the beginning of a crisis. Not a crisis of physics, but a crisis of wisdom. We have the fire. We have the technology. We have, for perhaps the first time in human history, a genuine path toward an energy system that does not depend on burning the accumulated carbon of hundreds of millions of years of geological time. But the path requires material, and that material does not come from nowhere. It comes from specific places, specific communities, specific ecosystems that have their own histories as long and layered as any human civilization. The Licanante people did not ask to be sitting above the most valuable brine deposit in the world. The flamingos of the Atacama did not choose to nest beside a resource that the global economy would one day decide it urgently needed. The question of how we extract lithium, how we use it, how we recover it, how we share the benefits and distribute the costs of the transition it is enabling, these are not technical questions. They are moral ones. And moral questions do not resolve themselves. They require choices. Every civilization that has ever existed has been defined, in some measure, by how it related to the energy it consumed. The civilizations that burned wood reshaped their forests. The civilizations that burned coal reshaped their skies. The civilization that burns oil has reshaped the climate of the entire planet. The civilization that will run on batteries is in the process of being defined right now, and the decisions being made about mining permits and recycling regulations and battery chemistry research funding and the rights of indigenous communities and the architecture of global supply chains. You are part of that civilization. The device in your hand is not neutral. It is a vote, however involuntary, however unconscious, for a particular way of organizing the world's energy and materials. The act of charging it participates in the system. The act of understanding that system, its history, its costs, its possibilities, is not academic. It is the minimum requirement for being a thoughtful participant in the world that is being built. Lithium connects us to the beginning of time. It also connects us to each other in ways we rarely see and almost never think about. To the geologist who mapped the deposit, to the worker who operates the pump, to the family whose spring has gone dry, to the engineer designing the recycling process, to the patient whose mind is stabilized by a tiny ion in their bloodstream, to the physicist watching plasma shimmer in a magnetic bottle in Provence. All of them are part of the same story. All of them are threads in the same goblin woven from cosmology, geology, warfare, medicine, engineering, and the stubbornly unresolved question of what kind of future we are willing to build and what price we are willing to pay for it. The flame that created everything now rests in your pocket. We borrow this spark for a brief time from the fire of the universe, and how we choose to use it, that is the only question that has ever really mattered.